there's a range here depending on how many microfarads the capacitor is. Just relax for a second. Here's what I'm talking about. If for example, well, let me explain this, the chart. So what you're looking at here is just a graph. This is just a chart printed on the paper. There's only one active part of this thing that you'll see, and that's an LED display. There's an LED display here. Let me just turn it on. You'll see it. Watch the bottom segment of the display. You'll see it flat. Just a second. Oh. All right. So there we go. So, it's a time delay. Anyway, so this, if you think of this as a thermometer, it's sort of upside down. Like a thermometer, the high numbers at the top and the low numbers at the bottom. In this case, the high numbers at the bottom, the low numbers at the top. So remember, low is good, low is good, low is good, right? So we want this LED bar graph to shoot up as high as possible. But depending on the type of capacitor, the microfarads of the capacitance of the capacitor, the ESR will vary. The normal ESR will vary. Here's what I mean. On the bottom, typical readings per capacitance. So here's like 1 microfarad, here's 10 microfarads, here's 100 microfarads, here's 470 microfarads, here's 2,200 microfarads. And over here is the number of ohms that you would expect if it's good or less. Remember, low is good. So the point that I'm making here is, let's say, for example, you have a 1 microfarad capacitor that you're testing, like an itty bitty one. To get it up into the green, meaning it's good, you could have as many as 4 ohms of resistance, and that would be good. Anything less, 4 ohms or less, would be good. Remember, low is good, low is good, low is good. Anything higher than 4 ohms, you would say it's bad. But if you had a 10 microfarad capacitor, here's 10 microfarads, to get it up into the green, you can have no more than 2 ohms of resistance. 10 microfarad capacitor is still a little dinky, tiny little capacitor. So 2 ohms. You get where this is going. The more microfarads you have, the lower its kind of base or normal ESR will be. So here's 100 microfarads. 100 microfarads. Oh, all the way up to here, man, you're not supposed to have. You're supposed to have as little as a quarter of a microfarad. Did I get that right? 100 microfarads. 100 microfarads. 100 microfarads. Yeah, to get up into the green, 0.25, right? So you can see that we have lots of capacitors that basically, when you test this capacitor, it should zip up to the top, shouldn't it, really? I mean, you're going to be testing lots and lots of capacitors that are 100 microfarads and 1,000 microfarads and stuff like that. So mostly you're looking for it to zip up all the way to the top. So kind of here's the way it works. So you take a look at the capacitor. Like this one says 68 microfarads. 68 microfarads. Stop. So on the chart, if we look, here's let's call it around 100, somewhere between 47 and 100, right? Zip, 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 zip. Here, it should really be pretty darn high. It should be somewhere in this region. When capacitors go bad, the difference is obvious. It's like it has like super high ESR. Let's see. I've never measured this one. Let's see what its ESR is. It's really old. It might be up there. Let's see. So on this particular device, it has this really cool tweezer probe thingy. And it enables me to really quickly probe a capacitor in circuit. The thing you're going to build this afternoon doesn't specifically have the tweezer probe, but there's a way around that using clip leads, and we'll talk about that when we build the thing. So despite the fact that one of these is red and one of them is black, it doesn't actually matter which one you put where. They only make this probe in half red and half black, but the actual test, it doesn't matter. Remember, capacitors have polarity, right? So, so all we have to do is figure out which two pins are the pins of the capacitor. Are you serious? Sorry, technical fault. I'm gonna have to restart. Sorry. Maybe you just can all see it. I think you probably can. Technical fault. Can you? If I put this here, can you all see it? Yeah. Can I see it? All right. So what I'm doing is obvious. On the bottom of the board is where the two pins stick out to the capacitor. You know what a capacitor is. You stuck a couple in yesterday. And all I'm doing is using the tweezer probe to go across those two pins. One of those pins looks kind of dark. So, oops. Oh, you're looking at the thing. Sorry. I confused them myself. So I'm just going across the bottom, across the capacitor pin.
She can't see.
Oh, come up here. Sit next to Pascal. He won't bite you. You won't? Promise. Pascal, don't promise.
Don't bite.
You're not going to bite? No bite. Pascal, no bite. Not food.
Stay.
Friend, not food. All right. All right. Okay, so you see we're way up here. Is it at the very tippy top? No, it's a half an ohm. For sure that capacitor is definitely good. I don't know what the heck happened to it. I have a capacitor that has, I have a power supply that has bad caps in it. Let's just check a couple of other capacitors just to see how they test. Maybe sorry. Oh, I see. My bad. So that one was definitely good. Here's another one. Way up at the top. So when you get a bad capacitor, it's really, really obvious. Its ESR is, it exceeds what's on the chart, but I mean it way exceeds it. It's just like, it's obvious that it's bad. Again, if it looks bad, it is bad, but just because it looks good does not mean it is good. You really have to test its ESR. So super important thing. Before you leave the class, I'll leave this up here. It's very important to take a photograph of this chart. The thing that you're going to build this afternoon will tell you a capacitor's ESR, but it won't give you the range where it's supposed to be. I mean, it'll be obvious when you have high ESR, but at the moment, it's not obvious to you. So make sure you take a picture of this chart with your camera phone and do that. All right, let me try to restart. This laptop has been around the world a few times.
Randy, how reliable is this meter that we're going to build with the ESR checks?
Boy, I don't know anything about reliability. It's a nifty kit, I gotta tell you. It's a really cool thing, and I see lots and lots of commercially available ESR meters that are obviously the same circuit. There's lots of variations of the same circuit, and I used a bunch of different ones in the class. This one is by far the best educationally, as you'll see when we start to build it. And it comes with a cabinet. It comes with a box. It's a really cool kit, and they're really cheap. They're like €13, so 13 euros.
There wouldn't be much incentive to buy that thing of yours, or find a similar one that you have.
No, that's why I give them away like candy in the class. I really want everybody to have an ESR meter. There's no reason why you shouldn't, and I don't see any reason that you need to buy a $200 meter. I'm just hyping it up, saying that this is by far the best thing I have ever had. And by the way, you're going to make one. I didn't mean to say you needed to buy this or you're doing that. So let me just see if I can invoke the camera magic here. Oh, camera genie, please turn on. Oh, there we go. Okay, so in your sample bag, you have 4 diodes, black cylindrical objects with a silver stripe at one end.
So Randy, in a nutshell, for me, to put it simple, when you testing a capacitor, you testing the resistance of the capacitor, always.
Yes, in a nutshell. And it's kind of hard for you to wrap your head around that at first. It's like, well, wait a minute, Randy, you're stupid. We're testing capacitor. It's rated in capacitance, Randy. You stupid guy. Why are you measuring resistance? But that's really what you do. And what's interesting about it is it actually measures its AC resistance. There's a unique feature of capacitors that we're going to talk about later on, where a capacitor will pass an alternating current signal through it, it'll pass it, but it'll block direct current. It's like, one of its like, one of the fields that does. So what that box does, it's a little more sophisticated. Well, yours does it too. Is to test the capacitor is it doesn't just charge up the capacitor and discharge it, time how long it takes to do that. It passes an alternating current signal through it and changes the frequency of that signal and sees how the capacitor responds. As the frequency of the signal goes up, the capacitor's resistance should drop. And it looks at a built-in, it does a table, and looks it up and says, a lookup table, this ESR is this. It's clever as hell. I mean, since there's so much need to have such a device, it's the one cool thing about now the modern electronic world is that the electronics is really cheap and it's capable. So anyway, we'll get back to that in just a little bit. So testing resistors, bad resistors, open circuit, or they go up in resistance. Bad capacitor, its ESR increases to something that we'll learn a lot more later, I guess, when we start testing. So if your failure is not in an electrolytic capacitor, which it is likely to be, by the way, in my opinion, really, honestly, 65-75% of everything I work on, power supplies, monitors, mostly I'm talking about, it's only electrolytic capacitor failure. There's other kinds of capacitors we'll look at, but it's the electrolytics that have this problem, and that's all it is. So you already kind of know what we're talking about here, and how hard is it to unsolder a capacitor and stick in a new one? It's not. The trick is finding the one bad capacitor that's bad, and that's cool. You replace that magic bullet and it works, but yeah.
So why is it that if those types of capacitors die all the time, why don't they have a replacement that doesn't die?
That's an excellent question. The lady in the audience says, is there, I'm repeating this to people at home. Is there a replacement? Well, when there is a replacement, I'll be out of business, I guess, because it means that things that won't fail, and there is, sort of. There is a modern solid state ceramic capacitor. It's the kind of capacitor they use in cell phones and stuff like that, that is sort of stacked and plated ceramic material and like that. Those do fail, but they fail less. And when they fail, they'll short circuit and get on, kind of burn up. So there is a modern replacement. The problem is packing enough capacitance in a small enough container. You can do a few microfarads in a teeny weeny container, but as you get up into 10 microfarads, the thing gets bigger. 100 microfarads gets bigger, and at one point it becomes like a skyscraper, an impractical amount of printed circuit board in what's known as modern surface device manufacturing, where the parts are just glued to the top of the board as opposed to the through holes that you just built yesterday. Excuse me. But it's a good question. Electrolytics are likely to be with us for a while. Now, how the Voyager spacecraft is still working 40 years later in deep space, does it not have any electrolytic capacitors in it? Maybe not. I really, I don't know how they built that thing, but, it's still running. But we can't keep a video game going forever on Earth. Capacitor failure is just like number one. But if it's not a capacitor failure, it's likely to be some sort of semiconductor failure. So we're going to spend the rest of our time here talking about semiconductors. Semiconductors are parts like diodes and transistors and things like that. Semiconductors are parts like diodes, transistors, and a kind of a special super duper transistor that we're going to look at later on, known as a MOSFET. We'll talk about all those things later on. So semiconductors belong to a kind of a group of family, like a family of components that are referred to as active. They're referred to as the active components in a circuit. They're called the active components. And what is meant by that is that these are the parts that are switching on and off. Sometimes they're on and they allow current to flow through them. Sometimes they're off and they're blocking the flow of current. Some parts can be like halfway on. Transistors can be all the way off. They can be all the way on, as I described to you yesterday, as a kind of a switch. Or a transistor can be any resistance from all the way off to all the way on. We're going to talk all about this. So they are what they're called active components. And because they're active and sometimes switching on and off, they fail. It's just, what makes them fail? I don't know. They work their butts off and they just eventually fail. Almost always, when a semiconductor fails, they almost always short circuit. Remember I said to you that resistors will always open circuit when they fail. Capacitors, likewise, when they fail, they don't short circuit. Electrolytic capacitors, let me be clear about that. Electrolytic capacitors, when they fail, they don't short circuit either. When electrolytic capacitors fail, their ESR increases, doesn't it? That's not a short circuit, that's just the opposite. It has more resistance when it fails. On the other hand, semiconductors almost always short circuit when they fail. And they almost always dead short. Like on your meter, if you were putting on that diode test that you used yesterday to play with the LED, if you happen to touch your leads to each other, it beeped. It's called a continuity beeper. Like when they fail, they're dead short. So finding bad semiconductors is almost always super easy using just your regular digital multimeter, just a regular meter, almost always. So semiconductors, just to reinforce, semiconductors almost always short circuit when they fail. The other stuff almost always open circuits or goes up in ohms when it fails. It's just really important knowledge as a technician because it kind of points you to the failure. If you're blowing a fuse, you've got to be looking at a bad semiconductor. How's a capacitor going to blow it? Well, I shouldn't say this. How is a high resistance going to blow the fuse? It's not. If a resistor opens circuits, it's not going to blow the fuse. But if the fuse is blown, it's got to be something that's short circuited. And so it just kind of helps you pinpoint the failure. So we're going to start with the simplest semiconductor, and that's these guys. And we sort of talked about diodes yesterday. We were talking about light emitting diodes, but these are regular, what we call conventional diodes. So let's start there. So the word or the name diode comes from the Greek word di, which means two, and ode, like electrode. It really means, like, in a practical sense, it means two leads. A diode is simply a semiconductor that has two leads. The schematic symbol for the diode looks like this. It's like an arrowhead with a bar on the end. Now, in the real world, this is filled in solid black. I'm really not going to do that, but on like a regular schematic, it's like filled in solid black. So a diode is simply a semiconductor that has two leads. We have names for the two leads. The lead on the left here, the lead on the left here is known as the anode, A-N-O-D-E, the anode. And the lead on the other side is called the cathode, just like we saw yesterday with the LED. They're called the anode and the cathode. We'll learn a lot more about cathodes when we start talking about monitors on Friday. If you look at the parts that you have in front of you, it's pretty obvious that the striped end is the cathode. So the striped end is the cathode, the non-striped end is the anode. And a diode is simply a one-way gate for electrons. That's all it is. It's just a semiconductor is just like a wire, but it only allows the current to flow in one direction. It's a pretty simple device, really. It took a lot to develop it. It's really a pretty simple device. So the current only flows in one direction. Guess which direction? Gee whiz. Current flows from positive to negative. So the diode itself, if you try to run the current through the other direction, it's an open circuit the other direction, and it just conducts in one direction. I want to put this diode in a kind of a sample example circuit to kind of show you how it works. This circuit isn't anything practical, it doesn't do anything, it just shows you how the diode works. Let's look at a simple schematic here. And the schematic consists of a battery, and we learned about that yesterday, right? Remember, the long lead is the positive terminal of the battery, and a lamp, battery, and a light bulb. Right? So you have to connect the battery up to the light bulb, so there's a wire that connects to the battery to the light bulb. We have a name for this wire. It's called the source path. The battery itself is referred to as the source. This thing is called the source. The source can be anything that's going to be pushing the electrons through the circuit. The source could be, in this case, a battery. It could be solar cells on the roof. It could be one of your magnificent turbines that are out here dotting the countryside, which are like fantastic things. They're just amazing. Hassan, if you ask him nicely, maybe even not so nicely, he should take you on a tour of his storage unit. He has a storage unit like somewhere nearby, and it's really is amazing inside. He has tons of stuff in there. But right across the parking lot, there's a gigantic turbine. Right, it's like right there. It's just anyway. So the source is anything that's providing the push in the circuit. In this case, it's a battery. But we have to have a way to carry the current from the source this way to the light bulb, which is referred to as the load. Anything that is using the current from the source we refer to as the load. Like in a video game, the source might be a power supply and the load is the logic board or something like that. But like anything that's using the power from the source, we refer to as the load. But you can't hook up anything with just one wire and expect it to work. I mean, everything has got to have really two wires, except for like a radio antenna. You pretty much always have two wires going to something. So you have to have not only a source path carrying the current from the source to the load, but you have to have this all-important return path. You have to have what we refer to as the return path. And the return path brings the current back from the load back to the source. And when we have all of those things, we have what we refer to as a complete circuit. It's a complete circuit. In order to have a complete circuit, you have to have four things. Number one, source. Number two, a source path. Number three, a load. And number four, really important, you have to have that all-important return path that brings the current back from the source to the load. So I'm going to build this circuit right now. I am going to break the source path. And I am going to connect a diode here. I am connecting the diode in series for the 10th time, right? In series with the light bulb, right? Anytime that current has to flow through one thing to get to another, they're said to be in series. So if I hook all this stuff up correctly, do you suppose the light bulb will be on or off?
Now it's on.
What do you think?
I think it's on.
On. It's on.
How many of you think it'll be on? Well, it will be on. Why? Well, current flows through the diode in one direction. The direction the arrow is pointing. Is not the current flowing in that direction?
I see, yeah.
Yes, it is. So it should be on. Well, let's hook it up, shall we? And let's prove that. So you remember from yesterday's experiment, I have this battery here, and the small terminal, as you know, is the positive terminal, and that's here on the red wire. I'm going to connect it to the diode. Am I going to connect it to the anode or the cathode, the source path? Am I going to connect it? He asks. To the anode. Thank you very much. And let's pick another color here. I'll use a yellow clip lead to connect the cathode to the lamp. And then remember, we still have one more connection, and that's the all-important return path. The return path is super important. We're going to be talking about this a lot as we go through the class. But guys, hey, gentlemen. So the return path is really important. We're going to be talking about this a lot as we go through the more sophisticated circuits. In that, well, we'll be talking about it a lot. So if I hook this up, let's see if it works. Oh, yes, it does. So as predicted, the light lights up. Let's find the diode. Here's the diode now. So let me turn the diode around here. And when we turn the diode around, it does not conduct. So remember, it's the polarity of the battery that determines which way the current flows. Current flows in a circuit from positive to negative, as you can see. That's the way the current really flows in the circuit. We had it hooked up like this, and it did light up. Now we've turned this thing around like this. Well, the current, let's turn off the light bulb. The current still wants to go in that direction, doesn't it? That's the way the battery is hooked up. But the diode's just now going, hey, buddy, no, you're not going through me. Instead of it being basically like a wire, it's a closed door now. It's just not letting any current through at all. Now, if I reverse the polarity of the battery, of course, it would. It would conduct again. If I left the diode all hooked up the way it is and just turned the battery, now the current would be flowing in the opposite direction, and ooh ah, it lights up. Right? So we have names for the two operating modes of the diode. And you need to know these names just because it's kind of well, you need to know these names. It's not hard. When a diode is conducting, when the current is flowing through it, like when I had first hooked up, the hotshot engineer guys have a name for this operating mode of the diode. The diode is said to be forward biased. Forward biased, B-I-A-S-E-D, forward biased. This word bias in electronics just means to put a certain voltage on something is to bias it. An engineer might bias a transistor at a certain fraction of a volt or something. You don't really care, but to bias something is just to put a voltage upon it, basically. So when the diode is conducting, the hotshot real engineer world refer to that diode as being forward biased. That's its operating mode. I would just say, hey, it's on, meaning it's conducting. On the other hand, when the diode was turned around so that the current wanted to go through it, but remember the diode is blocking it like this, we say that the diode is reversed, or really technically reverse biased, but it's reversed. Reverse bias, B-I-A-S-T-E, reverse bias, or you might just say it's off, meaning it's not conducting, it's not conducting at all. So where this will come into play momentarily, we're going to look at specifications, and you'll see where this comes into play in just a little bit. So the diode itself is made of these two different kinds of silicon. We talked about it yesterday. Remember, I passed around the chunk of silicon, and it was like, ooh, isn't that pretty? And it doesn't conduct electricity by itself. It's just an insulator. It's like a piece of glass, basically. It doesn't conduct electricity at all. So they had to change the atomic structure of it, and they changed it into two different polarities. There is a positive polarity and a negative polarity. And the diode is built like this. The diode right here is facing this direction, right there. So this is the anode, if you remember, anode, and this is the cathode. Right? So over here on the left-hand side of the diode, it is positive. It is what we call type P silicon. It is positive silicon. It is silicon that's treated with an element known as boron. You don't care about that. It's positive. Over on the other side here, the silicon is negative. Inside the diode, there's an itty-bitty, teeny little chip of silicon inside. Let me grab something here. Let me cut this diode in half here and show you what I mean. I guess I'm kind of standing in front of the TV. Can everybody see the TV okay? No. Let's see how close I can get. All right. So I'm going to chop this diode in half, and let's see what's inside. So I've chopped it in half, and this is what's inside. There you go. So you can see it's like a little square. It's kind of like a little square, and if the light was different, I think in here you can see it has sort of a crystalline nature. Let me focus this even closer here. Oh yeah, you can definitely see it. So remember the sample of silicon that I passed around here. Yeah, it looks like this. It is this. It's the same the same thing. Now what you're seeing here mostly though is inert plastic. The black part is not dye. The black part is just epoxy plastic. Let me chop that off and I'll show you what you're really looking at. Well, I want safety glasses. It always makes me scared. I'm scared of getting something in my eyeball here. There we go. I don't care if you get something in your eyeball. Almost done. All right. So what you really are looking at is this. Oh, jeez. Wait, I think we're okay here. Connecting to base unit. Earth to base unit. Oh, I see him late with brakes. Hang on a second. Ready to share? No, you're not getting off that easy. I'm almost done. What you're really looking at is this. Just this flat, like flangey, pancakey kind of thing. If I can hold it still. And you can see this little square. We call this a die. Like D-I-E, like, half of a pair of dice. And I really divided that thing right down the middle. So right down the middle, and this is important, wake up, wake up, wake up. Just give me one more minute here, we'll take a break. Right here, where the type P silicon meets the type N, is a really important thingy that you're going to test momentarily. And it's called the PN junction. It's called the PN junction. It is where the positive silicon joins the negative silicon. Hence, it's a junction. Where two things join, it's a junction, right? So it's called the PN junction. PN junction. PN junction. When we are testing transistors, this is what we're really doing. We're really looking inside the diode or whatever it is and examining the quality of this thing called the PN junction, and it's where the type P meets the type N. And when I sliced the thing in half, it broke right at that PN junction. It's predictable. I guess it's a weak spot or something, but I can do it all the time. You just kind of eyeball the middle, and that's where it just breaks in half. And that's the thing that fails. When a diode fails, it dead shorts across the PN junction. Right? So let's go back to that. Circuit that we just looked at. I know it's break time. Just give me a sec. We're almost done. Right? So again, we have the source path with the diode in series, the light itself, and the return path. So at the moment, I have this hooked up to a 9-volt battery. Question, not a trick question. What is the voltage at the anode of this diode? Not a trick question. 9 volts, right? Why? Well, it's hooked up to the battery. Of course it's 9 volts. That's actually a law of electronics. There's a law of electronics that states that the voltage on a wire is everywhere the same on a wire. So anyway, so it's hooked up. So over on this side, we'll have 9 volts. On this side over here,
8 not 4.
Sorry?
8 not 4.
You're ahead of me. On this side over here, the voltage will be only approximately 8.4 volts. There is approximately 0.6 of a volt or so that is used up or dropped, as we say, across this PN junction. And I can demonstrate that for you really easily. Let's hook this thing back up. So if you look at the brightness of the lamp here, right now the diode is forward biased, isn't it? Right? If the current is flowing through it, it's forward biased, meaning it's on. Watch the brightness of the lamp. I'm going to short out the diode, eliminating this tiny voltage drop. And you'll see that the lamp will get a little bit brighter. You can see it get a little dimmer and a little bit brighter. It's pretty obvious when I do that, right? So this small amount of voltage that is used up or dropped across a perfectly normal, that's a good working diode, right? We just tested it, in fact. Will be about 0.6 of a volt, and we can measure this with our meter. This is how you test semiconductors. This small amount of voltage drop here has a name. It's known as the junction drop. It's called the junction drop. It's called the junction drop, junction drop, junction drop. We are measuring the voltage that is dropped across a PN junction to see what it is. So whip out your meter and put it on the diode test, just like you did yesterday for testing the LED. Whip out your meter. Take your meter out. Remove your meter from your toolbox. Insert your meter leads into your meter. Set your meter to diode test setting. Please. So the way the meter works when it's testing diodes is that there is a battery in the meter. You know that because you put them in yourself. I got to write to the Chinese company that did that to me. That was almost bad. So there's a battery in the meter, and the meter shoots out some juice off the red meter lead and measures what's coming back on the black lead and shows you that on the display. We expect it to be somewhere around 0.6 of a volt when the diode is forward biased. So start with the red meter lead on the anode, the non-striped end. Put your black meter lead on the cathode, the striped end. Does your meter respond in some way? I don't care what the number is right now, but do you see it doing something?
Yeah.
Right? Everybody okay? Meter's doing something. You don't care what the number is right now. Now reverse your meter leads, or reverse the diode on your leads. You now get the overload reading, don't you? Right? So clearly the meter's it's doing something. The diode itself is doing something some way, and it's not doing anything the other way. And that pretty much defines a diode, doesn't it? So if you go back, flip it back over again, and get the actual reading, what are these meters showing you? 0.56? 0.5? Does it show you the decimal point?
Yeah.
Oh, okay, that's great. So that's what you expect. On the other hand, if you touch your meter leads to each other right now, he said, the meter's beeping at you, and it's just going, this diode is bad, it's shorted, right? I mean, that's the deal. Because 999 times out of 1,000, when a diode fails, it's dead short. I have seen open diodes, but open diodes, like flipper diodes, will break open. The vibration will just break them right open. And then without that flipper diode, it's a protection diode. It blows drivers on the printed circuit board. So I've seen them break open, and I've seen them burn open, where obviously to have burned, it must have shorted first, and then caught fire inside and then burned itself open. But the initial failure, the real failure, is always thanks to short circuits. So you can often most of the time, you can test a diode in circuit because it's an obvious short circuit. Does this make sense to everybody? Okay. So I apologize for the delay. Let's take a break.
Yeah. No, my controller helps with the element G07. But they still test the same?
Yes, they will still test the same.
Yeah. Alright,
They'll test the same. You can also make a bipolar cap if you don't have them. If you take two capacitors, put them in series, and join their negative leads together, so the two positive leads are on the end, you've made a bipolar cap. The thing is that you have to double the capacitance. Like, if I put two 10 microfarads in series, I end up with one 5 microfarad, which will replace a 4.7.
Sorry.
Yeah.
NVGNZ.
Alsjeblieft.
Do you hear already new things that you didn't know yet?
Yes,
Yeah. And the tips and the tricks and the diode, always short circuit.
that's right.
Conductor, always short, and the capacitor.
I mean, getting the theory is what's best, right? Because I always I know that if it beeps, it's going to go so wide. What
Yeah,
the
what's
function?
happening?
Exactly.
On what you're reading is, so if it doesn't read perfectly in circuit, what are you going to say? You're going to say, oh, it must be bad. You're going to take it out. You will always test it out in circuit. You go, oh, it's good, and put it back. And you'll do that half the time. That's how you troubleshoot stuff. I mean, on the easiest level, as I mentioned, the real super joy is to be able to think to yourself, do whatever test and go, it's that one for sure. But you're wrong a lot of the time. I don't even want to sound egotistical and say even me, because this isn't how I mean it, but even me with my experience, I take out lots of good stuff. Why agonize over it? If it doesn't test perfectly in circuit, just pull it out, test it, and put it back in. If you can solder, this takes us a few seconds, 15 seconds, 30 seconds.
And it's the same for the Zener and Trotsky.
Yeah, we haven't gotten there yet. We will.
It's the same.
Same test? Yeah.
It's
Yeah,
the
same
same
test, yeah. And same failure mode. The most important thing is the failure mode.
Thank you.
Is it an idea that today at 3 o'clock we stop with the class and go to the other place to show the class around? Did you manage to stop at 3 because there was a little misunderstanding with the educational programs that we have? It was supposed to be no educational program, but it appears to me that a group of kids will come at 3 o'clock.
Not in here though, but over
It's
there.
over there. Yeah, they'll have a program. So if we quit
Perfect
at
timing.
3, yeah, if we're quit at 3 today,
Yeah.
then we can go to the other place and
So it will be a good solution.
Senor. Great. Break. You have a break now?
Yeah, we're on break. With
Great.
But also no, the spelling is not the same.
Again?
The spelling by name is not the same as the arrow. So if I do the spelling of my name
Okay.
is not identical to the spelling of the name
Okay.
of the animal.
Okay.
It's not the animal.
Yeah. Okay.
It's named after it's a nickname that came from a video game character.
Okay.
It just kind of sort of, became my name.
Okay. Yeah, I just like things with I hear things.
I also love them for separate reasons.
Yeah.
I know too.
Yeah. Sometimes I just sit here and I just be like this, and then she goes like, no.
I think that's so confusing. like a big human big hand with a crowd thing, Yeah, there's someone there's something you can consider who has this rabbit that is such a march who's like and this rabbit gets like massaged every day and it will like
Yeah.
be massaged so much. I just love this rabbit so much.
She's really lovely. If I put her on the sofa with me, and she just jumps and she lays here, and then I need to put the
Yeah, all of my game things like just if I have my hands like this, they like to be like right here where the one part is, or they try to get right like but like with that one I can't stand up safely because and I was also had to put the nails. I had to just like, okay, you're getting in the crevice and then I miss having like little knives around, just little boots that just kind of, like I had my game picks when I was in the US. I had more space for them, and I like entirely just completely safe that they could only. Okay, the one singular time that I had my laptop with the mouse sit in there, I had the mouse unplugged, but I had a blanket on me, and the mouse was happened to the end of the blanket, and I didn't pay attention, and I thought you were messing with the carpet, I didn't know it's that. But I lifted up, and was like, hey dude, what are you doing? And he chewed that for him down.
I like it.
I was angry at him. Like, I was just like, why? Like, I should have recognized that he's not messing with my But
I'm in several groups on Facebook, and they all call it Spacey High. Hey, how do you say? Yeah, just because they love it, and they just they always make pictures and chords in several pieces.
I think the cool thing is, is that both guinea pigs and rabbits, they like to grab their food bowl and go, look, it's so annoying, it's so scary. I know people use like ceramics to prevent so they try to do it. Yeah, so
They have ceramic bowls that the food in, but one of them, all the night, you can hear it. It's like pulling it up and just making it loud noise.
gremlin.
What do you say?
Actually, it's a little gremlin.
Yeah.
A little bit
But he
nervous.
just likes to shake it, I guess. But it's always the ones, because they break it up when they chew on it, and then they want to have the full ones, I guess, and then he just shakes it up. He's a good deal. We have three, and it's a small one. He's only like that. He's 9 years, and we have one 10 years, and the other one she's 5.
They seem like they're probably perfectly normal, and I would love to just be along in this environment, I would love to see these things, I'm also the same person who likes to cow, the cows, sliver. You're like, so we love my bicycle. So I'm like,
Not meer dan zeg maar. Dat kunnen we dus op momenten, zeg maar.
oh,
Wanneer
like, they're lovely to death.
Cool. Does everybody know that?
Ja, dat is
Oh, cool.
we gaan er ook slag.
Well, I guess we should get going, huh?
Right?
Okay. Yeah, because the wolf
Hey.
sounds good.
Waarom moeten we het ook
Yeah, because at the other place you got lots of like and dash.
So, as you probably heard, Hassan's today going to take you over to that other facility I was describing to you earlier, which is great. It also means that this afternoon when you build the kit, you have to demonstrate your prowess in soldering, which some of us have proven beyond a shadow of a doubt in whipping this project out. And in fact, the assemblage of the plexiglass case seems to take as much time as actually building the thing. It's horrendously ill engineered and ill conceived with little tiny nuts. You need little Chinese hands to assemble the thing. But all you care about is building. So we'll see if it goes. So at 3 o'clock, he wants us to be out of here, and they're going to lock the door and they're going to let the kids in the other side of the side. Right? So, in the back of your blue book, your textbook, your blue book, way in the very back is the reference set, what I call the reference section of the book. And it's at page 384. Turn to page 384, please. 384. 384. 384. Yep. So remember, every time that we look at a new component, we're going to look at its specifications. We're going to look at its specifications. So let's take a look at diode specs. Diode specs. Diodes are basically rated by voltage and current. So rating number 1 is the voltage rating of the diode. The voltage rating of a diode is not how much voltage it puts out. The voltage rating of the diode is kind of like the voltage rating of a capacitor. It's the maximum voltage that in this case, that the diode can handle. In this case, it's the maximum voltage that the diode can block when it is reverse biased. Remember, when it's blocking it, it's called reverse bias. So when the diode is reverse biased, how much voltage can it handle? Remember, voltage is pressure. It's exactly the same thing. So can it handle 50 volts of pressure? Can it handle 100 volts or 400 volts? How much pressure can it handle when it is reverse biased? If you remember, the way that diode is built, what I showed you is it's a little tiny square chip like that. On one side is that flangey, pancakey thing that I showed you up close. I don't know what you flange, I guess you call it. On the other side, there's another one of those things that's hooked up to the leads. And then the whole thing is covered in all that black epoxy plastic. So the actual diode is the itty bitty thing inside. Why is it in such a big giant package? Heat dissipation. Semiconductors do not like to run hot. That's why very often you'll see them mounted on, as you know, an aluminum heat sink. These thin aluminum things are called heat sinks, as you know. And in the world of physics, to sink something means to suck it out. So it's a heat sink that sucks the heat out because semiconductors are kind of basically room temperature devices, sort of. I mean, not exactly. They can work when they're pretty cold, and they can work when they're pretty hot, but not super hot. That's why you have a cooler on your CPU and stuff like that. And in this case, the cooler is the actual black epoxy plastic. So when I broke this thing in half, I broke it right down the middle. Just like that, right where the PN junction, remember it's called the PN junction, is. It just broke right in half. Well, what the voltage rating of the diode is how much voltage can this thing block until it blasts across that real thin little layer, the PN junction, and blows up the diode. So that's what the voltage rating is of the diode. It's the maximum amount of voltage that the diode can block. It's the maximum voltage that the diode can block when it is reverse biased. Does that make sense? So remember how we could use a higher voltage capacitor as a replacement? Exact same thing here. Higher is okay. Higher is okay. It is perfectly okay to use a diode of a higher voltage rating, and you can go as high as you want. It doesn't affect that junction drop reading. I really don't know what makes something a higher voltage diode versus a lower voltage diode. My impression is that they kind of make them all the same, and they go into some sort of testing device that non-destructively tests the diode. But I really don't know. I don't really care. So that's specification number 1. We have a name for this specification. The voltage rating of a diode is not just called the voltage rating. It's known as the diode's PRV. The voltage rating of a diode is called the diode's peak reverse voltage. It's called the peak reverse voltage. PRV, or peak reverse voltage. That's the peak, the maximum peak. Reverse, meaning, remember, when it's reverse biased and blocking it, And voltage, voltage. So PRV. So that's specification number 1. Specification number 2 is the current rating of the diode. And that's the difference between the two sizes of the diodes that you have in your sample bag. In your sample bag, you have 1 amp diodes, that's the two small ones, and you have 3 amp size diodes, and that's the bigger one. And this is true of electronics in general. In general, the bigger something is, it's bigger because it handles more current. That's the deal. That's why some parts, semiconductors specifically, are bigger than other semiconductors. It's just how much current it can handle. It's just like, like water current. In the front of your house, you might have a big water main that's this big because it has to handle a lot of current and feed a lot of houses. But inside your house, you have little pipe because the current flows less. So it's the same thing with parts. So they're rated basically by voltage and current. The current rating of a diode is also the maximum. It's the maximum current that you can pass through the diode without it burning up. And just like with voltage, you can always use one of a higher current rating. It is perfectly okay to use a higher current rating diode under really all circumstances. The only difference is that if you look at the diameter of the component leads, the 1 amp lead is much thinner than the 3 amp lead, and you might have to make the hole in the board bigger to get a 3 amp diode in there. But especially with monitor repair, I typically don't carry 2 amp diodes. Remember I said I'm cheap and I don't want to buy a bunch of things I'm not going to use. I have 1 amp diodes and I have 3 amp diodes, but lots of monitors use 2 amp diodes. And if I find a blown diode, I just stick a 3 amp in there, but the lead doesn't exactly fit, so I just take a little tool of some sort and make the hole a little bigger. Away you go. So the current rating of a diode the specification is known as I. Remember they use I as the symbol for current because they thought of current as like intensity. So I, with a little letter O underneath, and as you guys probably know because you're smarter than Americans, that little letter O is known as a subscript. Subscript, and we use it in scientific notation to further describe what we mean by the big letter, like big letter I. Okay, well, what kind of current? I is current. What kind of current? Output current is what that stands for. Pronounced I sub O. So the subscript is always like smaller font and descended. Subscript, right? Subscript. So I sub O. So the current rating of a diode is known as its I sub O, and again, when you're making substitutions, you can substitute all you want. Just you can go up and both stay the same. There is one other specification that we're going to talk about tomorrow when we get into power supplies, and specifically into switch mode power supplies, and that is the speed of the diode. The speed of the diode. The diodes that you have and have given you in your package are what we refer to as conventional diodes. Conventional meaning ordinary, nothing special about them, just diodes. And they're more or less made to work on kind of low frequencies. But more modern electronics work on a much higher frequencies. An old-fashioned power supply in an old video game from the 80s, power supply is working off of 60 hertz, or 50 hertz in your case. And these work off of 50 kilohertz. So things are switching on and off much faster. So we have high-speed diodes. So as far as the speed is concerned, you either have, again, what's known as conventional, meaning ordinary, I wouldn't say slow, but ordinary speed diodes, or high speed. And again, we're going to talk more about that when we get into those power supplies tomorrow that use the high speed diodes. So it's really important that you understand a little bit about part numbering. So I just want to take a little bit of time here to talk about part numbers. when you start fixing electronics, you are now living in a world of part numbers. I mean, what's on the floor? You have zillions of part numbers, a lot of which now are obsolete because they're 40 years old, and a manufacturer, maybe they make it for 5 years, maybe, and then it becomes obsolete. Fortunately for us in the industry, in the arcade, I don't know, I guess it's still an industry. A lot of that stuff is still available as new old stock, but we did talk a little bit about counterfeits being an issue now. But so anyway, so there's lots of part numbers. So I want to take just a few minutes to talk about the part numbering system and kind of how it all works. So this thing that you see on this page here is known as a data sheet. This is an important word, data sheet. Data sheet. The data sheet is what the engineer uses to pick out which actual part number he's going to use when he designs a circuit. When an engineer designs a circuit, he knows he needs, for example, a diode of a certain voltage and a certain current and like that stuff. Okay, what's its part number? Where does he buy it? Where does he find this diode? That's what a data sheet is for. The data sheet allows him to look up the voltage rating and the current rating and see what the actual part number is. So there are a couple of part numbers, a bunch of part numbering systems, but there's a few main ones. The main part numbering system that we use in the United States happens to be called, and you don't need to know this, it happens to be called the JEDEC system. JEDEC. It happens to stand for Joint Electron Device Engineering Council. The story is that way back when I was a lad, way back when they first started making semiconductors, diodes and transistors and stuff like that, there were a whole bunch of different companies making the exact same part. That is, the part with the exact same specifications, but they all put their own part number on it. It might be, RCA, Synetics, Texas Instruments, whatever it is. They made diodes or whatever they made, and naturally they put their own part number on it, which makes a lot of sense. I mean, two different brands of automobiles might have the same fan belt specifications, but one doesn't call up the other and say, hey man, you want to share a part number? It'd be really fun. There's no communication like that. But it's a problem was a problem in the electronics industry because we used to have substitution guides constantly because thousands of parts were coming out all the time. Every 6 months or more, you'd have to go to a bookstore and buy a substitution thing that says that this part number is equal to that part number is equal to the other part number. It just wasn't practical. So they got together and formed this engineering council. A bunch of engineers got together and hammered out a part numbering system. So let's look at the part numbers on the parts that I've given you. So the two small diodes there are 1 amp diodes. What are the part numbers of those 1 amp diodes?
1M4007.
One of them is a 1N4007. What's the other one?
4004.
The other one is a 1N4004. And if you can't read those numbers, you need a magnifying glass. I really strongly suggest that you use some sort of optical augmentation, some kind of a magnifying glass to look for bad solder joints or read part numbers or whatever. Even if your eyes are really, really good, you can easily miss stuff and you can pick it up with a magnifying glass. I find lots of stuff with a magnifying glass. Anyway, so these diodes are both 1 amp diodes. 1 amp diodes. Right? The 1 in the part number means something. It has 1 PN junction. The first digit right there, in this case number 1, tells you the number of PN junctions, and we know that a diode just has 1. As you're going to see shortly, a transistor has 2 PN junctions in it, so transistors' part numbers often start with the number 2. For example, the transistors that you put in yesterday's kit, the part numbers were 2N3904. 2N because, as you're going to see again shortly, transistors have two PN junctions, which you will test just like you did the diode anyway. So the first number means that. The second number, N, just makes it look like a part number. It just means number. It's kind of silly in a way, but if the part number was just 14004, that's a number, but it doesn't look like a part number. But if you say something like is an NQ-407B, that's a part number. You know, you can tell. So in the American system, the JEDEC system, they just stuck an N in there to say, hey, this is a JEDEC number and what the number is. In Japan, we have lots of Japanese stuff, especially here. They have a similar system. It's known as the Japan Industrial Standard, or JIS. And like our system, the first number is the number of PN junctions. So diodes start with the number 1, and transistors start with the number 2. That's the number of PN junctions. But theirs is 1 or 2S. S for semiconductor, which kind of makes more sense. I mean, it still accomplishes the same thing. The Japan Industrial Standard is actually a little more sophisticated when you really look at it. And again, we're going to get into transistors shortly. But in the Japan Industrial Standard, they have transistor part numbers that are 2SA, 2SB, 2SC, and 2SD. 2SA and B are both what are known as PNP transistors. We covered that yesterday. The 2SC and 2SD are NPN transistors. In the JEDEC system, you can't tell if something's NPN or PNP by looking at the part number. But in the JIS, Japan Industrial Standard, you can, which is kind of cool. Additionally, the 2SA is a high frequency device that switches faster, and 2SB, I guess you'd say, is low or normal frequency. And same thing with C and D. The C is a higher switching speed capability than a 2SD. So it's a little more of a sophisticated system. Getting back to the JEDEC system, you cannot tell from the part number what the specifications are. In other words, the part number is just a number. It's meaningless. It doesn't mean that it's 4 amps, 7 volts, or something like that. It doesn't mean anything like that. That's the point of the data sheet. You will be Googling lots of data sheets. When you first start working on stuff, you're going to have bad parts, and you're going to say, okay, I know for sure this part is bad. What is it? You know, what are its specifications? So you're going to Google the word, you're going to Google whatever the part number is, 2N3904, or whatever it happens to be, followed by the word data sheet, and you'll get the data sheet back that, in this case, would tell you the voltage rating and the current rating. So, what is the voltage rating of the 1N4004? It's 400 volts, right? You know, the PRV, 400 volts, right? What is the voltage rating of the 4007? It's 1,000 volts, isn't it? Well, remember, I said that you can always use a diode of a higher voltage rating, and here's what I'm talking about. The 1N4004 is probably the world's most common diode. I mean, it's all over the place, especially in amusement games. Well, all over the world. It's just a super common diode. But since I can replace a diode with one of a higher voltage rating, if I'm like buying a bunch of diodes and they're cheap, so you buy 100 at a time, a lifetime supply of them, why should I buy 4004s, even though they're the most common, when I could buy 4007s, which can work for anything? We don't have anything that needs anything higher than 4007. They all have the same junction drop, and they cost about the same. So, within pennies of each other. So that's what I mean by like if you know how to substitute parts, that's real handy. You don't have to keep them all, or you don't have to keep them all in stock. Or if I was working on something that needed a 4004, oh, it's bad, but I don't have any of those. Can't I use a 4007? Of course I can. So you can always substitute, and again, of course, you can go up in current as well. So let's take a look at the other two diodes that you have. What are the part numbers on the other two? The other two diodes, the bigger ones.
5401.
So one of them is a 1N5401, and the other?
5404.
The other one's a 1N5404. Well, 5401, if you look it up, is like 100 volts. Is it not? I think it is. The 5404 is 400 volts. You know, same deal. So if, for example, I had a bad 5401, I could replace it with the 5404, couldn't I? You know, like no problem. So it's you know, it's really pretty simple. Does all that make sense? Everybody okay on that? So very often, oh, you know what? Just to get back in sync, let's just take a quick break. Let's just take a quick break, a quick 10-minute break, and then we'll be on sync for another hour.
So Randy, about diodes, the speed thing.
Yes.
I can forget the speed thing for now.
For now, yeah. When we tomorrow, I'll cover switched mode power supplies, and that's where you need the high speed diodes and the Peter Chow kind of, or even modern switching computer power supplies. Everything now. Unless you guys, I mean, are you guys okay? I could carry on. Nobody left, right? Right, we're all still here. Oh, all right. I'm good to go. I thought I was giving you guys a break, but I'm ready to go till noon. You guys all cool? Okay, all right. All right. So very often, if you turn to the next page, very often we need 4 diodes connected together in a circuit known as a bridge rectifier. A bridge rectifier. A bridge rectifier. You know, why it says rectifier bridges on that page, I really don't know. It's really called a bridge rectifier.
The book says bridge rectifier.
Where do you see the other?
On the data sheet, did I correct it?
Yeah, it's corrected in both.
Oh, really?
Yeah.
Did I really?
Yeah.
Oh, okay. Woo me! All right. Yeah, I don't know why this says that. So we're going to get into bridge rectifiers in great detail when we start looking at power supplies. But a bridge rectifier is simply a circuit made of 4 diodes. There are 2 diodes with their cathodes tied together, and there are 2 diodes with their anodes tied together. The purpose of the bridge rectifier, it does only one thing, is to change alternating current into direct current. Here's the deal. Diodes, another word for a diode is rectifier. The process of changing alternating current into direct current has a name, and the name is rectification. We will talk about this in great detail tomorrow, because that's the whole thing we're doing tomorrow is high power supplies. Here's the deal. Alternating current is really good for some things. Alternating current is really good for motors. Alternating current is really good for AC motors, weed whackers, toasters. Alternating current is also really good for heaters, like we talked about an electric heater with a nichrome wire. Uh, AC is really great for hair dryers and waffle makers, and especially if you live in Belgium. Does everyone have a waffle maker in Belgium? You probably do, don't you? You guys are nuts for waffles. Anyway, so it's really good for all that kind of stuff. But alternating current is not good for electronic stuff. Electronic stuff really requires direct current to operate. Now you may be saying to yourself, well, wait a minute, the games are plugged into the mains. Obviously they use AC, but really the first thing that happens is the AC hits some kind of a power supply, and the power supply takes the AC in and changes it into DC coming out, and that's what's really used to power everything. Alternating current is also really good because we can send it long distances. At the power generating station, they can raise the voltage really high, hundreds of thousands of volts, even higher, and transmit it over long distances. And then at the other end, the voltage is lowered back down. And by doing that, you reduce the amount of power loss in the wires. The wires themselves are made out of copper, and they have a certain amount of resistance, so you're going to lose power in the wires. By jacking up the voltage, you reduce the amount of current. Remember, two different things, voltage and current. By jacking the voltage really high, we can reduce the amount of current being drawn across the wires, and the lower the current is, the less there is power loss in the wires. The formula, you don't have to know this, is the power loss is equal to I squared, the current squared, times the resistance. So the resistance, we can't do anything about that. The wire is the resistance it is. But if the power loss is increased by the square of the current, so if we can reduce the current, we reduce the power loss. So you can thank a Croatian fellow named Nikola Tesla for that. He's the one that invented what's called the AC polyphase system. He's the man that changed the world. He should be your big hero of all time. He's not, unfortunately, because he's crazy. And in the end, he married a pigeon. So, like crazy man. But a great inventor.
Married a what?
Fellow. Married a pigeon.
Oh, pigeon.
Yeah, he went crazy. He was he always was crazy, actually. But in the end, there was this white pigeon that he was convinced was his wife. He never married, never had a girlfriend, never had any. Anyway, so we have to change the alternating current into direct current. The process of changing AC into DC, as I said, is called rectification. Hence, these things are known as rectifiers because that's their main duty. All rectifiers are diodes. I've been saying the word diode all morning, but the data sheet says rectifier. All diodes are rectifiers, but I'm sorry, all rectifiers are diodes, but not all diodes are rectifiers. That is to say, you will see lots of diodes in circuits that are not changing AC into DC. They're doing something else. There's lots of other things that diodes are used for, like the diodes that are across a flipper. They're not changing AC to DC. They're doing something completely different, and so on. So anyway, so it's called a bridge rectifier. So a bridge rectifier is simply four diodes hooked together, and its only function is to change AC to DC. While a single diode might be used for all kinds of different things, the bridge rectifier just changes AC to DC. So the mains comes in, it will pass through a fuse first always. That's the schematic symbol for a fuse, and connect to the bridge rectifier like that. Where the two cathodes come together, that's the positive output of the bridge rectifier. Where the two anodes are tied together, that's the negative output of the bridge rectifier. So you put in alternating current, you put in the mains voltage in here, and what comes out of this thing is direct current. And we'll see exactly how that works tomorrow. Testing the bridge rectifier is just like testing a regular diode. You just did it. Open one way, and remember, junction drop the other. The junction drop you expect to be around 0.6 of a volt. That's really just an average reading. The junction drop will typically be somewhere between 0.4 of a volt up to around 0.8 of a volt, 0.6 kind of being an average in between the two. So the junction drop might be 0.4, 0.5, 0.6, 0.7, 0.8. But regardless of what it is, when you reverse the leads, it will be an open lead, the overload lead. So bridge rectifiers can either be for individual diodes, or they can be a single one-piece bridge rectifier. Tomorrow we're going to look at a bunch of bridge rectifiers. You'll see how they work in a power supply. So there is another kind of a diode that you will encounter in the amusement biz of it's still modern day. Turn in the way back of the book, like the very last article in your book. And it's Understanding Zener Diodes. It's after the flow charts. It comes after page 420. It's not page 421. I just forgot to put it in the book, and I stuck it in the back of the book. And what I really want you to see is the data sheet on the next page. So if you turn the next page over, you'll see a data sheet that says, 1N4728 through 1N4764 Zener diode. Everybody with me on that? All right. There is another kind of a diode that we're going to talk about more tomorrow when we start looking at power supplies. And remember, I mentioned to you that when we start talking about power supplies tomorrow, I'm really starting on CRT monitors because that's where the power supply is. There's another kind of a diode that you encounter, which is a sometimes failure in our industry, and it's known as a Zener diode. Zener, or it might be pronounced Zener by some people. Zener diode. The schematic diagram, the schematic symbol for a Zener diode looks like a regular diode. It has a cathode and it has an anode. To show you that it's a Zener diode, you see a couple of little angular bits coming off the cathode bar that kind of form a Z for Zener, like that. It's called a Zener diode. So a Zener diode is a completely different animal from a conventional diode. It's only called a diode because it's a semiconductor with two leads. Remember, diode, right? Two leads. That's where the similarity ends. And you can really kind of tell that from looking at the data sheet. If you remember the voltage ratings we just saw for diodes, they were like 100 volts, 400 volts, 1,000 volts. These are crazy, kind of more specific. Really 5.1 volt, 6.2, 6.8, 10, 11, 12, 13. Obviously, this means something completely different. It's a completely different kind of a thing. So here's the way a Zener diode works. Let's just say, for the sake of discussion, that I have a 12-volt Zener diode. Common part number 1N4742. It's an extremely common Zener diode. You might even run into one. 12-volt Zener diode. So what this means is that, like a conventional diode, a Zener diode will pass current in the direction that the arrow points, but it doesn't do anything practical in that direction. we really virtually never, I know that there's an occasional exception, but not as far as we're concerned. Uh, there's just never any reason for us to run current through the diode in that direction. Instead, the way the diode works is that, like a conventional diode, this diode will block current from flowing in the opposite direction of the arrow, as long as it's less than the Zener voltage. In other words, if I tried to put 5 volts on the cathode of this thing, it would block it. 6 volts, 7, 8, 9, 10, block, 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 block. But if I exceed the Zener voltage, let's just say, for example, I put 13 volts on the cathode, now the Zener diode will conduct. And it's really the only semiconductor that conducts opposite the way the arrow points. I mean, it does conduct the way the arrow points, it's just not useful that way. But this one, we can get it to conduct opposite the way the arrow points if we exceed the Zener voltage. We call that an avalanche. It just avalanches, and that's another name for these things. They're called avalanche Zener diodes. So again, as long as it's less than the Zener voltage, it blocks it. If we exceed the Zener voltage, it does turn on, but it doesn't just turn into a wire. It doesn't just start instantly conducting and allowing everything through. It's a real selfish little thing. If you can kind of give human characteristics to an electronic component, the Zener diode wants to keep the voltage across itself constant at all times. It never wants it to exceed 12 volts, and it'll hold that voltage at 12 volts for itself. Anything that's left could come out the other side if we wanted to design something that way. Like, for example, in this case, if we put 13 volts on the cathode, it would keep 12, and we get 1 volt out that side. If we were to put, 100 volts on the cathode, it would keep 12, and we'd get like 88 volts out the other side. In other words, what this diode is a voltage regulator. We use Zener diodes in power supplies to establish a voltage reference and to regulate voltage. What I mean by that, and we'll go into this in great detail tomorrow, is that, like this, for example, is a 12-volt power supply. I put in 120 volts or 240 volts, and I get out 12 volts. How does it know? How does it know what 12 volts is? Something has to tell it what 12 volts is. It's not smart. Something has to tell it what 12 volts is. So we use Zener diodes as voltage references, where the power supply looks at the voltage reference and says, oh, that's what 12 volts is. Well, I'm going to adjust my output so that it's 12 volts, because that's what you're asking for. So it's a voltage regulator diode. The Zener diode, when you test it, it tests like a regular diode, open one way, junction drop the other, just like normal. When it fails, it will short circuit, just like a regular diode does. In this case, you cannot make substitutions. These voltage ratings are clearly very, very specific, and you can't change the voltage. If you change the voltage, you affect the output of the power supply. There's no telling what will happen. So you just go by part number. On a Zener diode, whatever the part number came out, that's what you're getting to put in. And that's the beauty of part numbers. You don't have to know anything about the specifics of the voltage rating or the current rating or dissipation or anything like that. You just give them a part number and label. Make sense to everybody? Okay. So now let's move on to transistors. And again, in your bag, let's pull out the transistors. And remember, you had 2 little transistors with the brown paper on the leads. And then you had 2 thingies in the TO220 package, only one of which is the actual transistor that we're talking about here. And its part number is TIP31. You have 2 little ones. One of them is NPN and one of them is PNP. So this particular package, if you remember, is called the TO220 package. If you recall, this particular package type, this number of this kind of package, no matter what's in this package, the package is called the TO220 package. As we will see later on in the class, what's in this package is not necessarily a transistor. It's just a package. We're going to talk more about that coming up. But the part number on that transistor happens to be a TIP31. That is not a standard JEDEC number. Remember, we just talked about the JEDEC part numbers, 1N, 2N, and so on. But this particular package was developed by Texas Instruments. So TIP, Texas Instruments package, TIP31. We use lots of transistors in this package, lots of transistors in this industry that start with TIP. In the electronic pinball machines, until we went to a more sophisticated system, it had banks and banks of TIP transistors in these same or similar packages. Anyway. So a transistor. So let's talk about transistors here. So a transistor is like a sandwich. A transistor is like the diode in that there is a p-n junction, which, by the way, is what the bar in the symbol represents. That bar that's at the end of the diode symbol is supposed to represent the p-n junction. Remember I said that the symbols kind of tell you what they look like or how they work. Well, all semiconductors have this bar in them that indicate this p-n junction. So that's the diode. The transistor is like a sandwich, as I mentioned yesterday. So it has two p-n junctions in it, and we're going to test them both. We're going to do that shortly, really. Two p-n junctions. So the way the transistor is built, if you remember the transistor schematic symbol, the NPN transistor looks like this, and the lead with the arrow on it, remember, is called the emitter. The lead on the same side as the emitter, the lead without the arrow, is called the collector. And over here is the controlling element that turns it on and off, and it's called the base. And in the in the TO220 package, if you remember, the leads are in alphabetical order, which makes it real handy and easy to remember. So from left to right, the left lead is the base, the center lead is the collector, and the right-hand lead is the emitter. So if you remember, the way the transistor works is pretty simple. All we do is put approximately 0.6 of a volt or so on the base of the transistor, and that causes the collector and emitter to connect together. I take the 0.6 of a volt away, and the collector and emitter are disconnected from each other. Now, in reality, a transistor can be anything from all the way off to all the way on. This will come into play a lot tomorrow when we start looking at the power supplies that are in monitors. The transistor can be all the way off. If I have no voltage on the base, the transistor is all the way off. If I put 0.6 of a volt on the base, it'll be all the way on. So what's really happening here is that a change in voltage on the base is being transferred into a change of resistance between the collector and the emitter. That's the actual derivation of the name transistor. The word transistor came from the term transfer resistor. As a change in voltage on the base is transferred into a change of resistance between the collector and the emitter. So they call it a transistor. So here's what I'm talking about. Let's say that you have 0 volts on the base. The resistance between the collector and emitter is now like infinite. We have infinite resistance between the collector and emitter. No current is flowing. Let's start to put voltage on the base. 0.1, 0.2, 0.3, really nothing happens at all. But at some point, as we start to increase the voltage on the base, the resistance there is going to drop from an infinite resistance down to, let's say, 1 megohm, 1 million ohms. Then I increase the voltage and current a little more, and now we have only 100 kiloohms, 100,000 ohms resistance between the collector and emitter. I keep increasing the voltage. Now I have only 1K between collector and emitter. You get where this is going until eventually I put whatever it takes on the base to turn it on fully, and the voltage between the collector and emitter drops to, or the resistance essentially drops to 0 ohms. Not totally 0 ohms. We'll get to that later. And that's really how the transistor actually works. So the transistor could be all the way off, or it can be all the way on. So when we test the transistor, we're really going to test two PN junctions. Two PN junctions. Give me 1 second to look in the book. Hang on 1 second. 1 second. 1 second. 1 second. So turn your book to page 57, please. 57, 57, 57. And let me just redraw this chart on the board here. Just take this second. So this first column of the chart is where you're going to put your red meter lead. Your red meter. Oh, that's really crappy. Oh yeah, but I have my own special awesome pens. Thank you. Thank you, but no thank you. I don't need your stupid Dutch pen. I got an American pen here. Watch how much better it is. There, isn't that beautiful? So the first column is where you're going to put your red meter lead, and that is the positive lead of the meter. The next column over is where you're going to put the black meter lead. And of course, that's the negative meter lead. And then the next two columns show what kind of a reading you'll get, whether it's an NPN or a PNP transistor. When we say that a transistor, when it is said that a transistor is NPN, what this means is that the base lead is made up, the base lead is NPN, sorry. What we mean, let me start over. What we mean when we say that a transistor is NPN is that the emitter is made of type N silicon. The base is made of type P silicon. And the collector is also made of type N silicon. And we have these two PN junctions that we're going to test. There's a PN junction between the base and emitter, and there's a PN junction between the base and collector, and we need to test them both just like we did with the diode earlier, 0.6 one way or so, and open in the other direction. Well, the base, whatever polarity is the base, if I put that meter lead on the base, it turns the transistor on. In other words, we're going to start the test with the red meter lead on the base, and we're going to put the black meter lead on the emitter. If this is an NPN transistor, at this point we will be getting the junction drop reading. And remember, when I say junction drop, what I mean is something between around 4/10 of a volt or 8/10 of a volt, or somewhere in between that. If it happens that you're working on a PNP transistor and testing it, at this point it will read open, the OL, the overload reading on your meter, because it's the opposite polarity transistor, right? So we're going to do this right now. I want to remind you that in the TO220 package, looks like this. The leads are in alphabetical order from left to right: base, collector, and emitter. But one very important thing to know about this package transistor and other similar packages is this. This is important. The way these things are built is it starts with a single piece of metal like that. If you remember the little square die of silicon that I showed you when I cut open the diode, a transistor looks the same. It's a little black square like that. It is bonded right to this piece of metal. Then there are a couple of thin gold wires that attach the die here to the base and the emitter leads. But the collector lead is the center leg. Those are one and the same thing. If it has a metal tab on the top, which ours does, there is continuity between the center leg and the metal tab on the top. They are both one and the same. So my point is that the center leg is the collector, so is the metal tab on the top. When you see these things mounted in circuit, you see them mounted on a heat sink like this, you will very often, almost always, see some sort of an insulator behind the transistor. Obviously the legs are broken off of this, but you see this gray silicone impregnated rubber is what that is. Some kind of an insulator behind the transistor, because the collector is the metal tab. So you don't want to attach the transistor right to the heatsink, because there may be more than one part on a heatsink and they don't want to talk to each other, so they have to be insulated. Or the heatsink might be grounded. It might not, but it might be grounded, and maybe you don't want to ground the collector of the transistor. So the metal tab is the collector, as is the center leg. Are we clear on that? It's the same. Alexia, are you with me? That's it.
What about bolt inside?
I'm glad you asked that question. What about the screw that's going through the middle of the thing? You are right on, man. So here's the deal. This is a great question. If you see between the screw and the heatsink, there is an insulated washer there, and it's super important, and it's called the shoulder washer. Let me show you on the board here. It's called the shoulder, like shoulder, S-H-O-U-L-D-E-R, the shoulder washer. And it looks like this. So it's made of nylon, which is an insulator. So this is the metal tab here. This is the metal tab here of the transistor itself. Then this is the heat sink, and here is the screw that is going into here. The washer is there to insulate the screw from the metal tab, which is the collector, right? Everybody with me on that? So especially on monitors, when you see transistors jammed on the side, there's always an insulator there. You have to remember the insulator, but if a shoulder washer came off, don't lose it, because you have to have the shoulder washer. You can't screw it in without you'll blow it up. Right? So let's start this test, shall we? Pull out your meter, put it on the diode test setting. and put the red meter lead on the base of the TIP31. Make sure you're on the TIP31 transistor. The other part is not a transistor. Put your meter on, and you can spread the legs if you want to, pull the legs apart. That's fine. Put your red meter lead on the far left-hand leg, which is the base. Put the black meter lead on the far right-hand leg, which is the emitter. This is an NPN transistor, so you should be getting a junction drop. Do you? 0.5, 0.6, something like that. Yes.
I still have a doubt with that screw because I've seen it like once or twice where it's with the insulated cap. So it's a must.
It's 100%.
It shouldn't have continuity between the base and the metal part.
You should
right?
not have continuity between the case, the metal case of the transistor,
If there
or the
is
metal tab.
then it's wrong. Correct.
You should never have continuity between the chassis and the collector of the transistor. Okay. So you should see a junction drop. If this had been a PNP transistor, you would have gotten an OL reading. The point that I'm making is you do not have to know if it's NPN or PNP to perform the test. You just have to know which lead is the base, the collector, and the emitter. And in fact, if the transistor is good, the test actually will tell you if it's NPN or PNP, because if the red lead is on the base, it's an NPN transistor, right? Okay, so leaving the red lead on the base, now let's move the black lead to the collector, which is the metal tab on the top or the center leg. You should also get a junction drop.
Is this super important, what you just tell us?
Critical. Yes, this is super important. Why? Were you asleep?
Well, I guess so.
I'm working on the lecture. We're almost there. Just hang on. Let me bring it together.
Okay.
Just relax. I'm coming. Just relax. Relax. It'll be fun. Not my first rodeo, right? Okay. So one more time, please. Humor me here. Leaving the red lead on the base, move the black to the collector, which is the center leg or the metal tab. Do you get a junction drop? Everybody okay on that? All right. Now, here's the important part. Is this critical? You're asking the right question. Is this critical? Notice the two numbers that you just got. Are they pretty close? Aren't they pretty close to each other? If you got 0.56, you got 0.56 on the other one, or something like that. So every now and then, I'll come across a transistor where those two numbers are not identical, or not that close. And I have to ask myself, it's still a junction drop. Is this part good or bad? And in the past, the way I handled this was, if I had another identical part, I would just test it. If it tests the same way, then that is normal. And I go, okay, I don't have to understand why that's normal. I just know it's normal. I do this a lot. You will have to teach yourself electronics a lot. You can always contact me, but you have to teach yourself electronics quite often. And one of the best ways to do it is by comparison. If you're fortunate enough to have more than one of the same thing, which I understand you may not, but you might, and you test one thing and you're just saying, gee, is this good or bad? I don't know. Let's perform the same test on the other thingy. Maybe you don't even know what the test is supposed to indicate, but if they both test the same way, how could one be bad and one be good? You get what I'm saying? They must both be good. So,
or both be bad.
So either that, or I would have to replace the part. If I found that those two numbers were kind of different, I would either get a new part and stick it in there, which is okay, or comparison test. But the cool thing is, the thing you're about to build this afternoon will XOR size the transistor. When you put a part of this thing you're about to build, it XOR sizes, not exercise like exercise, but XOR size, which means to operate. it actually operates the part. It puts a little voltage on the base, it measures what the resistance is doing, and tests it a bunch of different ways and says, yep, this part is working, or no, it failed to test. So this is a really valuable tool. It enables you to test all these parts without question. You'll know for sure if it's good or bad, not like, I don't know, is this good or bad? It's a definite kind of a thing. All right. So with the leads reversed now, I'm sorry. With the red lead on the base and the black on the collector, again, if it's NPN, you'll get a junction drop. If it's PNP, you'll get an open reading. Now let's reverse the leads, and we'll make the same test again, but this time with the black lead on the base. So put the black lead on the base, the far left-hand leg. Put the red meter lead on the emitter, which is the far right-hand leg, and now you should be getting the open reading. In other words, your reader's not doing anything, correct? And at this point, if it was a PNP transistor, this is when you would be getting the junction drop reading because it's a PNP. The base material is N, and the negative lead is the black lead. So it turns it on. So same thing again here. The base, keep the black lead on the base, move the red lead to the collector, which is the center leg, or the metal tab. And again, you'll be reading an open reading or an overload reading, where if this was PNP, it would be a junction drop. Okay, so we are now done with the base. We kind of use the base kind of as a center in a way. I mean, the way I look at it is, you're going from base to emitter, base to collector. Then you're reversing the leads, base to emitter, base to collector. But we're done with the base now. The final test is from collector to emitter. From collector to emitter is the main switchy part of the transistor. Remember from yesterday, it's like a wall switch. The collector and emitter are the two screws on the side of the switch. And when the toggle is off, which is the base, there's no connection between the two screws. And when the transistor is on, the two screws are connected together and current flows between the collector and emitter. We call that the collector current, I sub C. The current that flows in a transistor between the two screws, so to speak, from collector to emitter is called I sub C, the collector current. It's one of the specifications of the transistor, which we'll get to in just a little bit. Right? So, with the red meter lead on the collector and the black on the emitter, no matter what kind of a transistor it is, the connection should be open. Because the base is open. Because the base is hanging in the air, right? We're not hooked up to it. We have to juice up to the base to turn it on. So it's not being turned on. So it's open. And then you do have to reverse the leads. On the same, between the collector and emitter, you do it one way, it's open. You reverse the leads the other way, it's also open. And if it passes all 6 of those tests, it's good. If it fails any one of the tests, it's bad. And that's all there is to it. You can attempt to test transistors in circuit. Most of the time, they do not test good in circuit. Almost always, you have to unsolder a transistor and take it out of circuit in order to be absolutely positive that it's good and it's passing all the tests. And when you build the gizmo, if you have it out of circuit, which you will, you just throw it on the tester, test it. If it tests bad, you throw it away and get a new one. And if it tests good, you solder in a new part. You know how to solder, obviously. So, that's all there is to it. There's just nothing mysterious about it. So right now you have a way to test transistors, and this afternoon, right after lunch, you'll have another way. I would like, since he's feeding us, I'd like to cut our lunch short because he's going to take you away from me at 3 o'clock, right? And you're going to go visit we all are going to go visit the other place. So let's not take an hour to go downstairs and play games. Let's just eat and be back here at 12:30. Okay, can we do that? For sure. So let's take a look at transistor specifications here. So that's how you test it. Transistor specs. Transistors are rated a lot like diodes. They're rated like by voltage and current. So the voltage rating of a transistor, like a diode, you can always use one of a higher voltage rating. The voltage rating of a transistor isn't how much it puts out. Maximum. It's the maximum voltage that it can handle. It's the maximum voltage really that it can block when it's turned off, really. It's the maximum voltage it can handle. And again, it is possible to use one of a higher voltage rating. It's perfectly okay to do that. Higher is okay. It is perfectly okay to use a transistor of a higher voltage rating. They will be more expensive, so you don't want to do that if you don't have to. But if you, let's say, collect a bunch of junk and you need a transistor, so you're looking at the part numbers on some of your junk and you go, oh, what's the rating on this one? You Google the part number followed by the word data sheet. You get the specs and you say, oh, it's higher voltage. That's a good thing. It's not going to put out more voltage. It just means it could handle it if it was there, and it's not there. So we're good. So the voltage rating of a transistor is not just called the voltage rating. The voltage rating of the transistor is known as the voltage rating, V for voltage, V sub CEO. V for voltage, and the subscript is CEO. V sub CEO. And what this means is that this is the maximum voltage that the transistor can handle between the collector and the emitter with the base open, meaning not hooked up to anything. And as I just explained about 4 times, if the base is not hooked up to anything, the transistor is off, isn't it? Right? Because we have to put voltage on the base to turn it on. So if the base is open, meaning it's just hanging in the air, no voltage on it, the transistor is off, that's when it has a million billion ohms and it's blocking the current flow. How much voltage, pressure, voltage, right, can it handle? So it's called V sub CEO. That's one of the specifications. The next specification is the current rating. And again, it's the maximum. It's the maximum amount of current that the transistor can handle. It's the maximum amount of current that the transistor can handle between the collector and emitter when it's turned on and it's allowing the current to flow. Again, it follows the arrow. I mentioned to you before, that's known as I sub C, the collector current, I sub C. And again, it's a maximum. You know, how much current can it handle? 5 amps, 10 amps? How much current can it handle? And again, higher is okay. Higher is okay. It is perfectly okay to use a transistor of a higher current rating. You should stay with the same package type. That is to say, I could replace a tiny little TO92 package. That's the shape you used yesterday and the shape that is in your little bag of sample parts. That's the TO92. That's good for 1 amp of current. I could replace it with a TO220 package, and I've actually had to do it a couple of times in the field, but the pinout's different, and you got to Mickey Mouse it in there. You got to make the pins go different areas and put it in backwards and like that, and it's ugly as heck, but it works. But you shouldn't probably do that. You should stay with the same package type, really. But you can always use a transistor of a higher current rating as well. So that's the same as with the diode, right? You can always go up in voltage, you can go up in current, or both, right? But there's one more specification for a transistor. that the tester that you're going to build right after lunch will test. And it's an interesting specification, and it's called H sub FE. It's called H sub FE. H sub FE. And I have no idea what it stands for. I've read a bunch of different explanations of it. I'm not sure I trust any of them. I kind of know what it stands for. I know what it means, though. And here's what it means. H sub FE is a measurement of what's known as the gain of the transistor. The gain of the transistor. Or more correctly, it's called the current gain of the transistor. The current gain of the transistor. It has another name. It's also known as the beta of the transistor. It's called the current gain or the beta of the transistor. Beta being the second letter in the Greek alphabet. So here's the deal, and kind of put on your thinking cap. Remember I said that every day we're going to get kind of more and more complex, and this kind of gets into a little bit more complex transistor theory, but not a lot. There's a little bit of math involved, but not a lot. So I just need some room on the board. I'm just going to erase this. So I'm going to draw a simple circuit here. I'm going to draw a circuit kind of like what we just looked at, with the battery, which is our source, remember, the source path that carries the current to a light bulb. Only this time, I'm going to connect a transistor here in the return path of the light bulb. I have a transistor connected in the return path. If you remember, in a circuit, complete circuit, we have the source path, we have the load, and then we have the return path that carries the current back from the transistor back up to the battery. Right? Only I put this transistor in series with the lamp. If you remember, we had the diode up here before, right? But remember, I flipped it around and put it in the return. So anyway, so we have a transistor here. So if the transistor is off, no current will flow between the collector and the emitter, and the light bulb will be off. If I put 0.6 of a volt on the base of this, remember that's how it turns on, the transistor will turn on, and the current will flow from the source, through the light bulb, through the transistor, and back again, and the light bulb will light up. Is everybody sort of with me on there, right? So this is how we control stuff in the world of electronics, and we're going to see a lot of this tomorrow. Is our lunch here or something? Cool. In the world of electronics, if I want to turn something on and off, I could turn off the source, and it would go off, or I could turn off the return path, which is really how we do it most of the time. To control a load, turning a light bulb or a motor on and off, we leave the power hooked up to it all the time, but turn off the return path. It's just one of the ways that we can do things that we do. So let's just say, for the sake of discussion, that this transistor has a gain, a beta of 100. H sub Fe equals 100. Now that's not 100 amps or volts or ohms or anything like that. There's no dead guy associated with this thing. It's just a gain factor. It's just a gain factor of 100. So let's just say that this thing has a gain of 100. What that means is that if there is 1 amp of current flowing through the light bulb, let's say the light bulb takes an amp of current, it will take 1/100th of an amp on the base to drive it. The amount of current a transistor takes on the base to drive it depends on how big the load is. The bigger the load is, the more current the load draws, the more current we have to, we're not really shooting it into the base, but the more current the base will draw. If I put a bigger load on something, I need more current on the base, divided by the beta, or the gain of the transistor. If I took this exact same setup here, but changed the kind of transistor in it and made a transistor that had a gain of 1,000, it would only take 1/1000th of an amp, 1 milliamp, to drive it. In other words, the gain or the beta of the transistor is sort of a measurement of the transistor's ability to amplify. That is to say, how sensitive is the transistor? If the gain is high, if the beta is high, if it is a high gain transistor, it just takes a little bit of current on the base to drive it. If it's a low gain transistor, it requires more current on the base to drive it. So this is one of the specifications that the tester you're going to make after lunch will measure. It will actually measure the beta of the transistor. So not only does it exercise the thing and turn it on and off and make it operate and say, hey, yeah, it's operating for sure. Not only that, I've measured its beta, and I know that it is a beta of a certain amount. And if you looked up that beta in the data sheet, it would say that this is a normal range for beta, somewhere in that range. You don't care. You don't. In reality, you don't really care what the beta is, because as soon as you plug the part into your tester, if it's bad, it says it's bad, and you're done. And if it's good, well, it'll measure the beta if it's good, but it would be bad if it couldn't measure the beta, right? So we don't really care what the beta is. It's just one of those measurements you'll see momentarily when you build the thing. So let's go eat lunch, and let's start at 12:30. Okay, start at 12:30.
And for replacements?
Sorry.
And if you want to replace?
Oh, the beta has to be the same. The gain has to be the same. You can go up in voltage current, but the gain is the same.
Better can go better. Register is okay, but better change it.
You want to keep within. You can change the beta. You absolutely can. Almost any low gain transistor will substitute for any other low gain. For example, if the transistor came out was a beta of 100, but the one that was going in there was 120 or 130, it would be okay. 30-40%, I think, is probably fine. I think, but usually you don't have to. Well, you might have to because you exchange tank parts.
Waar kun je dit nou terugkijken ook?
Volgens mij wel. Ja, je kan hem switchen op.
Switch is
Ja.
ook terug te
Oké,
kijken.
dat vind ik wel leuk.